Hi everybody, the purpose of this video is to continue our talk on section 4.2, and here we are going to go ahead and discuss the addition rule for probability. Now in the previous video we talked about the properties of a probability measure. We talked a set theory, namely union, intersection, complements, and mutual exclusivity, and here we're going to straight on into the addition rule. So suppose that we have two events, E and F. The probability that event E or F occurs, in other words, the probability of the union of E and F is going to be equal to the probability of E plus the probability of F minus the probability of E and F. Now why is the case? Because it turns out that if you have elements that are in both E and F, when you compute these, you're double counting. So you need to subtract them out once. Let me show you exactly what I mean. Here's our the example we left off in the previous video, the card example. Let's call this the event E, okay? The probability of this event is 1350 seconds. And notice it has a 4 of clubs. The probability of event F is drawing a 4. There were 4 possible outcomes. The probability of this is equal to 450 seconds. Notice that this also has a 4 of clubs. So when we add these two together, we are actually adding these twice. So as a consequence, we need to subtract one of them out. So here is E and F, basically contains the 4 clubs. And if we just added these two together, we would get the wrong result. But if we add the probability of E and the probability of F, and then subtract out their intersection, we get the correct result. Okay, let's look at this from a different point of view. So this is basically just following the rule. Let's just take a look at what the union of E and F would look like. Okay, remember the union is essentially those elements, is a set that contains all the elements in both sets, contains all of the elements in both sets. So here is E, has 13 elements. Here is F. It has 4 elements, and of course they both have a 4 club. So when we compute the union, we don't write that down twice. So E union F has 16, not 17, but 16 elements, and that is why the probability of E union F is 1650 seconds and 4/13. The main thing is that when you use this particular rule, you need to subtract out those things that are common between both elements. Okay, and let's take a look at this in a die experiment. Suppose that we roll a die and observe the outcome. Okay, and let's let E be all even numbers, 2, 4, and 6. The probability associated with E is 3/6, or a half. But usually when you're doing these computations, it's best not to reduce your fractions until the end. Let F be the numbers 2, 3, 4, and 5. The probability of F is going to be 4/6. And if that's the case, then their intersection is going to be 2 and 4, which is 2/6. So using our probability rule, the probability of E or F is going to be the probability of E, 3/6, plus the probability of F, 4/6, minus the probability of E and F, which is 2/6, which will give you a total of 5/6. Does it make sense? Well, actually it does. This is the set E or F, or the set E union F. It contains 1, 2, 3, 4, 5 elements. If you did not subtract out the 2 and the 4 that we had before, we would actually have a number greater than 1, which would not be a probability. Okay, now let's take a look at a slightly more challenging problem that we will have to deal with. This is example 7. A box contains 14 large marbles and 14 small marbles. Each marble is either green or white. 7 of the large marbles are green and 9 of the small marbles are white. If a marble is randomly selected from the box, what is the probability that it is small or green? So we want to find the probability that our marble is small or green. Okay, so we have large marbles, we have small marbles. Okay, we have out of the large marbles, and we know that we have a total of 14 here and a total of 14 here, which means the size of our sample space is going to be 28. Okay, now we do know that there are out of the large marbles, 7 of them are green. That's supposed to be a 7, by the way. If that's the case, then the other 7 have to be white. Okay, now for the small marbles, we know that 9 of them are white. Therefore, the other 5 have to be green. 9 plus 5 is 14. So, using our probability rule, the probability of drawing a small marble or a green marble is going to be equal to the probability of drawing a small marble plus the probability of drawing a green marble minus the probability of drawing a small and green marble. The probability of drawing a small marble is going to be equal to the number of small marbles you have divided by the total number of marbles. That is going to be 14 over 28. We could reduce that to 1/2, but we probably don't want to at this point. The probability of drawing a green marble is going to be equal to the number of green marbles we have divided by t. Now we have 7 large marbles that are green plus 5 small marbles that are green divided by 28. So that will be 12 over 28. And then finally, the probability of drawing a small, I'm going to just use that for and green marble is going to be equal to the number of marbles that are small and green divided by t. And the number of marbles that are small and green is 5. 5 divided by 28. Let's put these together. Probability is small is 14 over 28. Probability of green is 12 over 28. And the probability minus the probability of small and green is 5 over 28. 14 plus 12 is 26, minus 5 is 21. This is equal to 21 over 28. Notice that they both have a common factor of 7, so this will reduce to 3/4. Or if you want to write this as a decimal, it would be 0.7. Whoops. Okay, so either of these two answers would be acceptable. Okay, and this brings us to our last example. A gym group fitness classifies its fitness class attendees by class and member status. The marketing team has gathered data from a random month in which there were 2,033 class attendees. Now, the first thing we want to realize here is that the size of our sample space is equal to 2,033, not 20,033. The other thing that you also want to realize is that all of these are mutually exclusive. There is nobody that is taking a bar class and a boot camp at the same time. Okay, and also you can't be a member and a non-member. So all of these are mutually exclusive. Okay, so with that in mind, let's take a look at what's going on here. What is the probability that a class is attended by a non-member of the gym and is attending a bar class, or is a member of the gym and is attending a yoga class? Okay, now remember, all of these are mutually exclusive, so the intersection between any two events will be the empty set, and the probability of their intersection will always be 0. So the probability that a non-member is attending a bar class is going to be equal to this number right here, 282, divided by 2033. Okay? The probability of a member attending a yoga class is going to be equal to this value right here, 209 divided by 2033. Normally, we would have that we would have that the probability of a non-member that's taking the bar class, or a member taking a yoga class would be equal to the probability of the non-member taking the bar class plus the probability of the member taking the yoga class minus the probability of its intersection. But remember, in this particular case, the intersection happens to be equal to 0. So this is going to be nothing more than the sum of these two values. And I'm kind of running out of space here, so I'm going to try to squeeze it in right here. That is going to be 282 divided by 2033 plus 209 divided by 2033. And that will give us 491 divided by 2033. And that is actually the reduced form, or as a decimal, you can write this as 0.2415. So that is how we do our the first part. And this brings us to our last question, or our last example. What is the probability that an attendee does not attend a spinning class? This is one where we could possibly use complements, because if an attendee does not attend a spinning class, then that means that attendee is either in the and here we don't care about membership. That means the attendee is either in the yoga class, the boxing class, the boot camp class, or the bar class. So instead of computing all of this, it might be better to compute the probability that an attendee is in spinning class, then the probability that he's not in spinning class, that would be its complement, is going to be 1 minus the probability of him being in spinning class. So let's go ahead and do that. The probability of an attendee being in spinning class is going to be equal to the probability that he's a member in spinning class plus the probability that it's a non-member in spinning class minus the probability of all the members that are in the intersection of all the members that are in spinning class and all the non-members that are in spinning class. Okay, once again, these are all mutually exclusive, so this will be equal to 0. Now, over here, the number of members the number of members that are in spinning class happens to be 98. So that's going to be 98 divided by 2033 plus 273 divided by 2033, and that will give us 371 divided by 2033. Therefore, the probability of an attendee not attending spinning class is going to be equal to 1 minus 371 over 2033. The best way to write that would be 2033 over 2033 minus 371 over 2033, and that will give us 1662 divided by 2033, which is a reduced fraction, or if you want to write this as a decimal, this would be 0.8175. And that is all that I have for this particular video. Stay tuned for a subsequent video which will go over your homework. Until then, if you have any questions, please feel free to contact me. This is Bob Boyle, signing off.